All right, good afternoon. Hi, everybody. So when you get a chance, just bring your homework up, put it on the table. We'll talk about it next week. So actually, before you turn it in, take a picture of it with your phones if you have not already, so you have some sort of copy to take a look back over. Because I don't think I'll be able to get it back to you in time, and I'd like for you to be able to look at what you did compared to what the solutions are, and go with me in that manner. So take a minute to do that. I don't see any up here. So just fold the leaves over as best you can. Cool. Oh, she's got a stapler if you want to use that. Thank you.
You should have. I didn't know this class.
Do you have a stapler?
I do not.
Alright.
She was offering one.
What?
So she was offering.
Oh, you don't mind? My printer will only print it like this.
Okay, that's fine. All right. So a lot of you guys are sophomores, right? A lot of you. So I was talking with a sophomore earlier this week, and I realized a lot of you missed completely first year of college on campus, right? So this year you're sort of scrambling to get used to being on campus, class to class stuff. It used to be online. I feel like, obviously going into college, going into your first year, there's a big change in how courses are run, but I feel like being on campus also makes a big difference. You guys feeling the same? Especially with IDA coming through, disrupting everything. So I had a renewed appreciation there for what you guys are going through, because I know that's a big part of the adjustment. Like, wait, where do I need to be now? And do I have time for lunch or whatever, it's tough. So hope you guys are surviving it and are learning to deal with it, okay? A couple notes here just about class in general before we get going. We are here, and we are looking at 2 more classes plus today's before an exam review. We'll go through the homeworks and any questions you guys have, and then I'll have our first exam on the 7th. So that's the plan. Right now, how I have it written is reactions and then reactions in reactors, and then just the reactors. I kind of flipping that, so just in case you're curious, this one's going to be changed to more kinetics analysis. Might get to that a little bit next time as well. So it might, depending on just the way I feel things are going after today, next lecture might just be mostly practice problems working together, or some combination of that, and an Excel primer to give you a few skills to use when solving these things. So I have to decide on those 2, but we can expect to do most of the reaction stuff this time, have some more practice, and some Excel work, both of which should help on your homework, which will be due. I'll post it tonight. It'll be due on the 5th. Okay? Does that sound good? All right. Okay, so last time we left off talking about the different type of reactors, and I was a little bit vague with what do we do with them mathematically, because I wanted to set aside today to do that. So we said there was 3 main types. We've got batch reactors, we've got batch reactors with a hose coming in and a hose going out, so the CSTR, and just a hose itself acting as a reactor. So those are the 3, the plug flow reactor, the continuously stirred reactor, or some people will say continuously mixed flow reactor. I think different books will say different things, but it's kind of the same point. You'll see a batch, you'll see something that looks like CMF-STR or something, maybe CMRs, completely mixed reactor, some form of that, and then a plug flow reactor, meaning the same thing, or the different versions of this meaning the same thing. We've got a completely mixed chamber with inflow and outflow. Okay, so we're going to start and get into the reactions inside a reactor, and we're basically going to take a look at, first of all, the simplest case, which is the batch reactor. So if we do have a reaction term, so far we've kind of pretended there's no reaction or considered systems that don't have a reaction. Today we're going to add that in. So with our typical accumulation mass balance here, in the volume we have some change in concentration per time, dc dt, and in a batch case it'll be 0 minus 0 because we have nothing, no input rate, no output rate, and then it's going to be plus any growth equations, reactions, minus any decay. Okay, and that'll be our net accumulation within the batch of water or batch of air. Okay, so I'm going to mostly be talking about it from sort of a water context, but the same applies, and we'll have a homework problem or two with air quality, where we're taking a look at a system that's acting in this manner, and just keep in mind that it can be either system, that there's no real reason it can't be one or the other. Okay, so with that, I want to talk about the reactions themselves. So when we describe reactions, one of the most important aspects of a reaction is what we call the reaction order. That is describing to us not just the rate, because we have a rate constant that tells us the rate at which it's happening, but it's going to be how that rate, the overall rate, depends on how much stuff you have there right now. Okay? The easiest analogy here is a bank account. If you have a bank account that's charging you a $10 fee every month, that's a flat amount taken away. We could call that like a removal process, or maybe a decay reaction. So we've got a flat amount every time. Does not depend on how much you have in there. You might have $20, you might have $200,000. Doesn't matter, it's just taking 10 out away each time. That's a good example of a zero order rate. And what that would look like if we're looking at, let's say, concentration of money over time, or of some chemical, for a decay, it would look like a straight line that's heading downwards, right? So that's, if I drew that perfectly straight, that would be a zero order decay reaction. Or we could have a growth reaction, and it would be obviously growing at some rate. Doesn't matter how much is in there, it's just going to keep growing. It's a linear fashion. For a first order, we have exponential increase. So again, coming back to our analogy, in a bank account, if you're earning interest, then you have an exponential increase over time. So the growth here, and I'll come back to this rate equation here in a moment, but the growth is going to happen. You're going to have a higher amount of growth every month or every year based on how much you have in there. So if you're earning interest, you started, let's say you're earning 1% interest and you have $100, you earn $1. If you have $100,000 and you're earning 1%, then you're earning $1,000, right? It depends on how much you have in there. So that's what we call a first order rate. Will look something like that. Of course, you can also have a decay reaction. Draw that in red. Would look something like that. Now, one thing you'll notice here is there's a very handy way on the math side of things that we can determine the order, or how we can describe the order. That is this rate equation here that's saying the rate at which C changes. That rate is going to be dc dt, and that's going to be plus or minus, depending on growth or decay, K, the rate constant, times C, whatever concentration we're dealing with, to the n power, where n is either 0, 1, or 2, depending on our reaction order. Technically, there's somewhere in between in some cases. We're not going to deal with that. We're barely going to even touch second order, but I'm going to tell you a little bit about it. They're pretty uncommon. So if you look at this for a zero order reaction, the rate, this dc dt, is equal to just plus or minus k, because c to the 0 is 1, right? So it just ends up being k times c to the 0, or just plus or minus k. So for a zero order, that c, that amount of money you have in the bank, the concentration of the stuff you have in solution or in air, does not matter. It's irrelevant to the reaction. You just have a reaction, it's producing stuff, it's decaying stuff, whatever, until you run out of it, I guess. Until you hit the 0 down here. Whereas for the first order, since it's exponential, and it'll be very familiar, we'll derive this, but it'll look like, our C is going to be equal to what we started with times e to the minus kt. We'll derive that in a minute, but you've seen that before. This is essentially a first order decay reaction in a batch system. And what you'll notice is you'll never truly hit 0 with a reaction like this, because it's always decreasing based on a percentage of what you've got. Okay? It's always going to be approaching 0, given that it's exponential. And of course, if it was a growth equation, it's going to be the same with a positive there. Okay, so that's the difference between zero order and first order. It does not matter what type of reactor you put them in, they're going to act that way. And the starting point is right here. So no matter what type of reaction you have, this term goes into this spot, right? And if you have multiple reactions, you would add them in just like you would if you had two different inputs, you would put two different input terms there. So keep in mind, this can happen, any type of reaction can happen in any type of reactor. Those two concepts are separate. Might be a checking account, might be a savings account, doesn't matter what the reactor looks like. Okay, the second order reactions depend on the amount there to a squared power. So in this case, dc dt equals plus or minus kc squared. And so there are certain reactions, chemical reactions especially, if we talk about atmospheric chemistry, there's actually a lot in that context, radicals that react so quickly, they will recombine with neighbor radicals, recombine with oxygen. They'll just combine with so many things that it depends to a square on themselves. It's like you have some amount of these radicals reacting, and so it depends on how many you have, but it also depends on how many you have, again, because they will react with each other. So it becomes a second order rather than just a first order. And these tend to be much more dramatically, dramatically sloped. So power law for these. Of course, it will depend on the rate constants you have and all of that. But that's sort of what you could expect from a growth or decay reaction like that. Okay, does that make sense so far? There's different reaction orders. Doesn't matter if it's chemical, a physical reaction, particles sticking together we could describe as a reaction. Doesn't matter what type of reaction we're talking about. We're not even really into our unit on chemistry yet. Certainly can be chemical reactions, but it can be other stuff. And the reactions, their order is going to describe how they look. And then there's one other thing it does. It tells us the units for the reaction. So, or for the reaction rate constant. So if we take a look at this rate here the rate at which C is changing. We can see there's clear units, right? It's dC dt. So that's going to be a concentration per time. And when we put it in a reactor and we're doing a mass balance on mass per time, what we're also going to do, if this is mass per time, we've got mass per time, then what we need to do is take volume, so this reaction is happening in some volume, times this concentration, which is mass per volume per time, so that the volumes will cancel and we get mass per time. Okay, so when we put it in there, we add the volume term because it's in that volume. We'll talk more about that. I'll show you very clearly what we're doing there. Point being, anytime we're doing this, these units, the dC dt, have to match the units here. So if we take a look and the C drops away in the zero order case, K has to be in the same units as dC dt. So we know if we see a rate constant with the units of dC dt, which is concentration per time, then we know that's a zero order reaction. If we see some reaction that has a rate constant that matches the case when it's first order, C to the power of 1, well, that's dC. We have a C on the left and the right, so the C's cancel. And then we're just left with per time, so dt on the bottom. So when K is in units of per time, that's a first order reaction, because it has to be, because that's the time when these units make sense. Right? That's the case where these units make sense. Okay, so we'll see different reaction rate constants, different units for them, and that actually gives us a lot of information based on this derivation. So watch for that as you go through. That order there is really important, and it's important for several reasons, and it gives us a lot of information about our system. Again, watching the units, paying attention, close attention to the units here. Okay. So let me elaborate on each of those a little bit more. So we said that for a zero order reaction, we have some C, which is our concentration. Let's call it milligrams per liter for this case. We have some rate constant, K. As I mentioned, that's going to be in those concentration per time units. So in this case, we'll take time as seconds. So then the rate constant must be milligrams per liter per second. Okay. Again, that's coming because the dC dt in this case would be milligrams per liter per second. And so that must be equal to K times 1. So that means K is then in milligrams per liter per second. Okay, does that make sense? Good on that? Okay. Another thing I want to show you here is we talked about the rate at which C is changing for a zero order case. Would look like that for a decay reaction, or reverse for a growth reaction. Well, if you take a derivative of that, you take the derivative of dC dt, or you take dC dt rather, that dC dt is going to be flat, right? That's just like going from velocity to acceleration, right? The acceleration is constant when we have if going from a change in distance over time, if we take the integral of that, we get the velocity, right, which is flat. If I said that right. You get it. You get what I mean. So we can do that same analysis here and look at the fact that this, if this dC dt is the velocity term, so to speak, that's not changing over time. There's no acceleration. It's another analogy for you that the math works out that way. Okay, so if we take a first order reaction, again, this is going to be that first order decay. It'll look something like that. Here we have units for dC dt. Again, this has to be milligrams per liter per second. That means that K So K times C to the 1 power also has to have milligrams per liter per second. And we see that we've got milligrams per liter on the C. That leaves us for the K needs to be 1 over seconds. So you'll see all over the place, you'll see a rate constant written as something something seconds to the -1 or minutes to the -1 or something like that. A good analogy here is, again, a bank account. You've seen interest rates all over the place. You've seen them on billboards, you've seen them on whatever. They've been around and in your life all the time, and you never really thought about it, but what they're actually saying is, oh, this is 5% APR. What that means is annual percent return or whatever. It's an annual basis. It's actually some number per year. Or maybe you do a monthly one, and it's per month. But oftentimes it's 10%, whatever. And a lot of times people just leave it at 10%, but it's really 10% per year. That's the per time basis. So you've actually seen this in your life all over the place, and hopefully today we'll take a look at this math and be like, I see exactly why that works now the way it does and why it matters, how much you might have in that account. Okay, so if you take dc dt in this case, when the C looks like that, you'll get a straight line, but it's going to be, in this case, your change in concentration is decreasing over time in a linear fashion. Okay, so when you integrate the function from a first order one, you get what looks to be a zero order one, right? So that's, again, just the way you can change from acceleration to velocity and so on. Same thing occurs here. You can integrate that, put it in this form, and you'll get a straight line that way. Second order reactions, again, we're not going to deal too much with these, and I'll show you why, because the calculus gets a little bit more intense. And it's just we don't deal with too many of them in reality anyway. But we can do the same units analysis here, and we can say that, well, dc dt, again, if we're using the same example, milligrams per liter per second, that doesn't change. That means K times C squared has to have those units, right? So what we have is milligrams squared over liters squared, and so K has to satisfy whatever it takes to get back to milligrams per liter per second. So we need a per second on the bottom. So if we take a look at the units for K, we know we're going to have seconds down here. We also need to get rid of one of the milligrams and one of the liters, right? So we just need a liters on top and a milligrams on bottom. So it's liters per milligram per second will satisfy our units. So it's kind of like flipped upside down in a way. So it looks similar to a zero order. So don't get confused there. Pay attention to where these units are being derived from, that rate order, so that you can know if you're given a problem and it doesn't specify this is first order or zero order or whatever, you can know something about the actual rates here. Okay, and again, this one is going to look like a very sharp decrease. And then if you were to integrate that, you'll get kind of that first order exponential. All right, any questions or issues dealing with the rates or their units, rate constant units? All right. I used milligrams per liter here and seconds as times. You really can use whatever you want, right? Could be money per year, could be coronavirus particles in the air per minute. Whatever you need to describe, you can describe with some rate like that. Okay, so let me back up one step. So I wanted to describe these reactions inside batch reactors because batch reactors are the simpler case. So we have no inputs, no outputs, just that growth or decay. We will elaborate on this in a moment, but essentially what we can do now that we see something about these rate orders, what we'll take a look at in a moment is for a given volume, we want to know that mass accumulation rate, right? We're looking at some mass accumulation rate, so we have to take the volume times dc dt, so we're performing it in some volume. This is going to be equal to, let's say, in a let's give an example of a first order decay. This would be negative k times c to the 1 power, right? So then, and all of this is happening in some volume. So in a batch case, those volume terms are going to cancel. So volumes divide out. We're left with dc dt equals minus kc. And then we can integrate. So we'll do this in a moment, but you can see how you could do that differently if you had c to the 0 versus c to the 1 versus c to the 2. That mass balance process that was just really quick, putting it in the reactor like this, is very simple in the batch case. So everything I already described is pretty much all you need to know for batch case, just about. We will derive this in a moment, but I want to compare that process with putting it into a CSTR. So for a CSTR, we know that if we have some accumulation, let's say V dc dt, and sometimes this will be 0, right? If at steady state, this term will be 0. We can't have steady state with a batch system unless there's no reaction happening, right? There's no inputs and outputs. I guess if you have a growth equation and a decay reaction competing, maybe you could get steady state that way with reactions. So I guess I lied. But most of the time for a batch scenario, we're going to look at one reaction and we're going to watch how that changes in the system. In this case here, V times dc dt, that's our accumulation term. It's going to be, let's say, Q times C in minus Q times C going out, because we have Q here and C, and we have Q, that's C naught, and Q and C over here in some volume, and we have some reaction with a rate constant K inside. Then we're going to have plus or minus in that volume some reaction, some K times C to the n power, depending on what our reaction order is. Okay? So the only thing we've done here is just simply elaborated on the reaction itself based on something we know about the reaction. And so far, all I've given you is that it's some reaction. I haven't even given you the order. We kept the n in there. So depending on the order, that's going to change the way this math works out. So if we're at steady state, then it could be 0 equals all this. If we're not at steady state, we have to leave it in there. Then if we have a first order, then we have the c in this last term. If it's 0 order, the c goes away because it's c to the 0. So the specifics of how your mass balances will work out is going to depend on your reaction order. Okay? We've already talked about it. It will depend on the steady state thing. We'll come back to that maybe in a little more detail next time. Right now, for the most part, we'll just assume that we have a steady state system. So that means our accumulation is 0. Then we have QC naught minus QC plus or minus VKC to the n power. I'll rewrite that. All right, does that make sense? Do you at least kind of get where the pieces are coming from, hopefully? Okay, great. A plug flow reactor, I talked about this last time, but essentially we can treat the plug as a little batch reactor that's going to go shooting through the system and come out the other end. So what that means is if we know what happens in a batch reactor, which we just described as relatively simple, then we can know what's going to happen in a plug flow reactor. Because all we need to know is, well, this plug is going to stay in this reactor for some amount of time. So it's just going to float through the system. It's like a little beaker on a conveyor belt. It's just going to be there until it pours out of the reactor. And so it's as if we had a batch reactor for some time, which is our theta, our hydraulic residence time. So otherwise, it works very simply like a batch reactor, and we can say in our infinitely small little plug there, we have a dc dt equals volume times plus or minus this kc to the n power. So it's just like the batch reactor, except that this is for time is equal to the amount of time it spends in the reactor, which is theta, right? And remember, that's V over Q. So if we know something about the reactor, we know the theta, then we can know how long it's going to spend in there, and we're done. We could also maybe be solving for the volume required or the hydraulic residence time required, something like that. So maybe we know some outcome we need 99% removal of something, and then we could say, okay, well, what retention time do we need to accomplish that? So how long does this batch reactor have to be running through the system until we achieve that goal? That's how we would solve it. So the plug flow reactors are nice and simple in that manner, just remembering that the time component is going to be that residence time. Okay, so I want to derive a few equations here for you. And it might be worth taking a look for yourself and seeing, can you do this derivation? So we want a batch case. So we just have a batch of water, it's well mixed. We're going to start with a zero order decay example. The rate here is described by dc dt equals negative k times c to the 0 power, like we described. And what I want is some c equals question mark. Or if you wanted to, c divided by some initial c that we started with. Okay, so take a moment and challenge yourself to think about how you solve this problem. Okay, so the approach would be to integrate this Fortunately, it's going to be simple, especially with the zero order case. So once I've written this out, hopefully you can jog your memory and say, oh, okay, this is the very basics of derivations or integrations. We have integral of dc from some initial condition to some final condition. That's going to be c minus c naught on the left side, and on the right side, this is going to be negative k times t minus 0, right? Because we go from time 0 to time t, and so this is minus kt. Okay, so in this case, it's pretty simple to get a c. That's going to be c equals c naught minus kt. In this term, in this way, c divided by c naught is a little more algebraically complicated, so let's not bother. But you could potentially do that relationship. You could find it. Sometimes we're interested in that, like what fraction is remaining. But that's a simple case, batch case here, deriving the mass balance that you would need in case you wanted to know something about the starting condition or the ending condition or how long it took. Remember, this is where we're going with the y equals mx plus b sort of thing, right? We just have to derive the y equals mx plus b, and then we can solve for whichever part we need, given our system, right? So this is the mass balance, or a form of the mass balance, that we derive for a zero-order decay reaction in a batch system. Okay? So take a moment and see if you can remember the integration trick that you're going to need for this case, the first-order case. It's a trick you've learned before. I'll cover it for you again in a moment, but it's the same process for the integration. You just need a different integration tool. So see if you can remember that, and then we'll derive it for you. Okay, so the first thing to remember is that you can get the terms on each other's side. You get dc with c, so you divide both sides by c. This, by the way, again, this is happening in some volume, but the volumes cancel for the batch case. So I wrote that back up here just to be precise. So we have dc over c equals negative k dt. So on the right-hand side, that's going to be pretty much the same thing as we saw a moment ago, from 0 to t. On the left side, we have something slightly different, again, from c naught to c. So we know that whatever it is, it's equal to minus kt. On the left side, the integral of 1 over c dc, or maybe if I say 1 over x dx, that might strike your memory like, oh wait, there's something there. That's the natural log of x. So in this case, we've got the natural log of c minus the natural log of c naught, because we went from c naught to c. So that's the one little bit of calculus that you need to remember for a first order derivation here. So with that, we can say there's an algebra trick here where we can combine the natural logs. You could kind of get this if you decided to raise everything to the power of e to the power of both sides, but this is the same thing as writing the natural log of c over c naught. So like I said a minute ago, if we want c, or sometimes we might want c over c naught, what fraction remains? This is pretty handy because now we're just about there. We have the natural log of c over c naught equal to minus kt. And then we can just take e to the power of both sides. We get rid of the natural log. We get c over c naught equals e to the minus kt. Or we could say c equals c naught times e to the minus kt. And this is your PERT equation that you probably learned in algebra for interest rates. This time we derived it from mass balance principles. Okay, does that make sense? May have even done this in a format sometime. But I wanted to be elaborate with it so that we can kind of be ready to deal with it in other contexts as well. So again, this is the same process for a plug flow reactor, except we're going to substitute the time for our theta, our hydraulic resonance time. For a CSTR, the system becomes a little different. Right now, what I'm going to do is say, let's keep this at steady state. Did you need a moment, or did you have a question or anything?
No, I just didn't know what the zero order and the first big cap.
Yeah, so this is a zero order on the left side and a first order on the right. Okay. And of course, I do post these to Moodle. Sometimes it's not the same day, or occasionally it's even a couple days later, but I will post them, and I'll make sure to have all the notes posted a little more quickly for the exam as it approaches. So you'll have all that to study from, as well as the recordings. Okay, for the CSTR case, we're going to assume this is steady state, although maybe we'll take a look at, we'll derive it to begin with as if it's not, and then we'll make that assumption and make it clear how that plays in. But essentially, this is always good to draw the reactor. We've got some well-mixed chamber. We've got a flow coming in and a flow going out. Something inside, could be air, could be water. Our general equation still remains accumulation is inputs minus outputs plus reactions. And in this case, the rate itself, the rate term, nothing changed, right? The rate term does not depend on the reactor. So that part doesn't change. What's going to change is the context within which we're putting it. So the accumulation rate, we'll just go ahead and write it out. VDC dt is equal to the Q C naught minus QC. And then we have, in this case, we're doing a zero order decay reaction. So this will be minus K times V, so it's in some volume. Again, remember, we need the terms to be, the units need to match throughout this whole equation. Otherwise, we're not able to do so. So Q times C, that's a flow rate times the concentration. That's going to get rid of that volume term, and it's going to just be mass per time. So mass per time minus mass per time, that means this guy has to be mass per time. And we know the units for K are going to be, for a first order, because it's C to the 0 power, that's going to be mass per volume per time, so we multiply that by the volume of the system, and we're left with mass per time. So that would be like milligrams per liter per second times liters. Okay, just making sure that's clear, and I've shown that again. Okay, so C to the 0, that's just 1, get rid of that. If we assume steady state, this goes to 0. Because the net accumulation is 0. It's pretty common to operate a system in that manner because it's easier to manage, and we kind of know we have a stable system and we know how much we're removing. We wanted to remove that much. We designed it for that, so we're just operating it that way, continuously removing some amount of bacteria or growing some amount of stuff. So a lot of times we'll do steady state. Probably take a look at non-steady state, but right now let's keep it here at 0 equals QC naught minus QC minus KV. Now, at this point, and you could recognize if we didn't do that, we'd have some integral that we'd have to solve, right? Maybe we can simplify things a little bit, but at the end of the day, there's some integral. So this time, let's go ahead again and solve for C. I'm using this as an example, solving for C. That's probably the most common, but not, maybe someday we'll solve for V or something else. Yeah.
Or, are we going to be given these like equations in the exam, or do we have to know them?
So the question is, for those online, are we going to be given these equations on the exam, or do you need to know them? I need you to be able to derive these, because you're going to need to be able to do that to accomplish the problems. If I do give you them on the exam, what it'll be is I'll write up the equation, but I won't tell you if this is first order decay or zero order growth or whatever in a CSTR. So even if I do give them to you, which I'll think about, I might do that. I will give you an equation sheet, but I'm not going to label them, oh, this is a zero order decay in a CSTR, right? You would have to recognize that part. So you're going to have to be able to work a mass balance to the point where you can understand, okay, is this the growth equation or is this the decay equation? Is this the derivation for a batch reactor or a CSTR, which turns out those look very different, so that's not so hard. But I'm gonna put that task on you guys. You could memorize them or use whatever I give you on the equation sheets, but you need to be able to do this. And I don't think you need to do like as elaborate as I've done, but I'm being elaborate so you get the whole process. That is my hope. Okay, so let's solve this for C. Again, at this point you could solve it for whatever, maybe flow rate or something. But for C, we have a C over here and Q's in two of the terms. So let's go ahead and simplify by dividing everything by Q. So we have 0 equals C naught minus C minus K times V divided by Q. V divided by Q is theta. So this is minus K theta. So what I did here was divide everything by Q. Right? Okay, so from there, we can just add C to the other side. So C equals C naught minus K theta. So not too bad there. I'm going to go ahead and have you guys try the derivation for the first order decay here in a CSTR at steady state. Okay, so hopefully you're starting at this point where we say steady state, so that accumulation term goes to 0. You got the input rate minus the output rate and that reaction rate. So hopefully that makes sense that we're inputting here in that volume. We've got this reaction times c to the 1 power. So the reaction is k times c to the 1 power. Yeah. Okay. Okay. So from there, again, we could decide on different things to solve for. Just for consistency, I'm going to say we'll look for C again. Essentially, this same simplification process is nice, just to divide everything by Q. It's a decent place to start. Of course, you don't have to, but I like to do that. So 0 equals C naught minus C minus theta K C. And this time we have C's in 2 groups. I'm going to go ahead and put those 2 on the left side. Really, it's just algebra after you get this set up nicely. If you're left with a dc/dt like in a non-steady state system, then maybe there's this calculus step involved. But if it's going to be anything at all complicated, I'm going to give you that step of it, right? So in your derivations for that first order batch reaction, you should know that. You should be able to do that. But anything more complicated for like a non-steady state system, I'm going to help you out, or it's going to be a steady state, essentially, on an example. Okay, so in this case, we've got C over here. We added the C there. We're going to add this other term, C plus theta Kc equals C naught. We can take the C out of these terms, 1 plus do 1 plus K theta, or theta K, equals C naught. And then our end term then is C equals C naught over 1 plus theta K. Or if you'd like, we can also do C over C naught equals 1 over 1 plus theta K. So pretty nice and simple there. All right. This is the type of thing that I might give you, but I do expect you to kind of know, okay, hey, this is specifically the first order decay mass balance when solved for C or C over C naught in a CSTR at steady state, right? That's a lot of conditions to memorize along with the equation. So if I do give it to you, I want to warn you right now that you're going to need to know those parts too, right? This is a common one. You'll see this a lot. But someday I might take a system that you've seen in a CSTR and then ask you about a batch case. You're going to be able to handle that change, right? Or maybe I ask you something with a plug flow reactor and then followed by one. Like, what do you do? So we'll talk a little more about sequencing them later. But you need to have this knowledge of where the derivations are coming from, because it's coming from the mass balance principles. Okay, the other thing that I have not done here is I've not done any growth equations. Again, the decay equations are the simpler ones, but I would encourage you to take a look, do this on your own time for a growth equation, right? It should be relatively simple, flipping a sign, right? But then track how it goes through the system with algebra, right? In this case, it would be, let me use a different color real quick. If we were to do the 0 order here, that would be a plus. That means that would be a plus. And then it should just be that, right, for a growth. For the equation over here, probably be like that. This would be a minus, and then you'd end up with a minus there. So it's not necessarily entirely intuitive, but it should be the same exact process with the sign flipped, starting with the sign flip, that is. So go ahead and do that as a study tools to make sure that you can do a problem with one of these with a growth equation instead of decay equation, even though we didn't directly go through that. Okay, with that, I'd like to have you work on a problem here. It might be worth doing the problem once with no reaction if you're not feeling comfortable with it, making sure you've got that part of it, and then doing it with the reaction. But right now, what I'll say is let's just take a look. I'll read it with you, and then give you some time to apply what we just learned to this problem. So here we are considering a 10 times 10 to the 6 cubic meter lake fed by a polluted stream having a flow rate 5 cubic meters per second and a pollutant concentration equal to 10 milligrams per liter. There's also a sewage outfall, so we've got two input rates here, that discharges half a cubic meter per second of wastewater having a pollutant concentration of 100 milligrams per liter. The stream and the sewage wastes have a decay coefficient, a rate coefficient of 0.2 per day. Assuming the pollutant is completely mixed in the lake, and assuming no evaporation or other water losses or gains, find the steady state pollutant concentration in the lake. So lots of stuff there. A couple things to note before you launch into it. Did say steady state, that helps out, that simplifies this thing. We see a rate constant here, and we're given the units even though they didn't tell us the type of rate, the order of the rate. So you should be able to know the rate order from that. The drawing pretty much takes the rest of it. It did say it is completely mixed, so this is going to act like a CSTR. In fact, you could draw it simpler if you wanted to and say, okay, this is a CSTR with two different inputs. It's completely mixed, has some volume and some reaction rate constant. Is that big enough for you guys to see, or do you need the picture larger? Okay. So hopefully you've had a chance to give that a shot, see how far you get. I went ahead and started up here with part of the solution saying, well, we need CM. That was kind of our question. And in doing so, we also need the flow rate. Well, there was no other inputs or outputs of water, so the flow rate, the new flow rate is just the initial two combined. That's the stream plus the outfall here. So that's 5.5 cubic meters per second. And then I took our mass balance that I wrote up here. And again, this is kind of exemplary of why I want you guys to be comfortable deriving a mass balance, understanding when I tell you steady state, this term's going to 0, yada, yada. So then I just wrote it, and I had it written out this way, and I said, well, I could just add those two terms that have CM in them to the other side. So I did QM, CM, VK, CM. This time I'm not dividing everything by Q because that doesn't really make sense with different Q's involved. I just left them in there. Otherwise, it's pretty similar, taking the same kind of similar form as the other derivation. So we have CM. We divide this QM V plus VK, so we extracted the CM out of that. Divided that by both sides. We end up with QSCS plus QWCW divided by QM plus VK. And all of that works out pretty nicely, except once you start looking at, double checking your units here, the K that was given was in per day, 0.2 per day. The Q here is in cubic meters per second. The volume is in cubic meters. So in order for those two units to turn out and work out properly, we need to convert either all of the flow rates into days or convert that rate constant in per seconds. So I decided to convert the rate constant per seconds. You can multiply it by 1 day, divided by 24 hours, divided by 60 minutes per hour, divided by 60 seconds per minute. I happen to have done that too many times, so I remembered that that's 86,400 seconds in 1 day. I feel like there might be a song about that or something too, but anyway, if you do that, you can convert from per days to per seconds, and then you've got 2.31 times 10 to the minus 6 per second for your rate constant. So just a 1 unit conversion there. Then really it's just plugging in the numbers from there. And so that's what I did in Excel. Relatively simple here. I kind of put all the terms. Expand it a little bit. I wrote in all the terms. I even kind of started here with the mass balance, converted the K, and then I said my concentration here, it should be milligrams per liter, is going to be equal to that equation that we just derived. And if we check, this should be QSCS. Not going to have you focus on all that, but really I'm just taking from the QS, the CS, the QW, CW, divide by that Q mixed plus the K times the volume there. And what we ended with was 3.49 milligrams per liter. Okay, so you could do that with a reaction or with a system that has no reaction. And you could even have a steady state because you have some going in and some going out, right? So you could solve that with no reaction, compare that with a reaction. That might be worth doing just to be comfortable with, comfortable with this type of system and how to manipulate it. Okay, so with that, let's just do a very quick Kahoot. I'll try to make something more interesting for next time. Let's just go ahead and grab attendance, and then I'll let you go. Any questions while we're at this? Oops. Have you guys been going back to the videos at all yet, or just kind of waiting for exams?
I downloaded the PowerPoints.
And by the way, if you wanted the blank PowerPoints, you can download them and just delete the writing if you wanted to like use it to solve something on your own. It's pretty easy. You just select it. It should select the box of scribbles and just hit delete. Do you guys like this format compared to other classes?
I like to do. I love to do this.
These?
Yeah, they're so fun.
Okay. Yeah, I have a whole bunch prepared for a different class, and I'm trying to. Sometimes there might be a different topic mixed in, so I don't have all the good ones for you guys necessarily. I want to spend a little more time for that. Okay, I'm gonna go ahead and start. If you didn't get in, just let me know. Like, I'll have you send me an email or something. All right, and if you didn't, please do turn in your homework. Go enjoy the nice weather and have a good weekend.
How were we supposed to know that this was the first order?
It's in the, so since it's per day, it has to be first order because K times the C, those units together have to always be the concentration per time. Because if you remember dCdt, that's concentration per time. So when we take the rate term over there and put in the rate term, all of this has to end up as, well, mass per time when you include the volume, but concentration per time if that volume term, if you didn't put the volume in. So in order for K to satisfy that, it has to be per time if it's first order. Then if you see it's per day, that means that is the units of K. That means C has to be the power of 1, which means it has to be first order.
Okay. Thank you.
Mm-hmm.
Hi.
Yeah.
On Tuesday,